And so what happens then, if v is very, very small compared to the speed of light, then v squared over c squared is going to approach 0, and 1 minus 0 equals 1, which means that your observed speed down here is, I should say the value of your adjustment factor, the square root of 1, is just 1, and so nothing changes. So if we look at this equation for how much does light appear to change as you approach the speed of light, what we're going to be saying here is that there basically is no apparent change in time when you're going slow, when v is very much less than the speed of light. Now, let's consider what happens if v approaches the speed of light. When v approaches the speed of light, then the numerator squared over the denominator squared begins to approach 1. And 1 minus 1 is 0, so this whole term goes to 0. And when this denominator goes to 0, this term here goes to infinity. So if we apply this to time, this means that as v approaches the speed of light, your time appears to become infinite. It appears to dilate. It appears to slow down and slow down and slow down, and almost appear to stop from somebody else's perspective that's not moving at that speed. And so we use the term proper time. Proper time is the time interval between the two events as measured by an observer who sees the events occur at the same position. So time dilation is a very real phenomenon. It's not just a trick of mathematics or an interesting philosophical idea. We have actually calculated the fact that some of our astronauts who have been out in space and have traveled at certainly not speeds anywhere close to the speed of light, but have been traveled at pretty high speeds for lengthy periods of time, indeed actually come back and are several seconds or minutes younger than their counterpart. And we've also seen that in some of our experiments with subatomic physics, like with the study of muons. And this has been confirmed over and over again by all kinds of experiments, including using our super collider in CERN in Geneva, Switzerland. And here's a math problem that you could do in order to see just how much that change in time from an event that should have taken 3 seconds, if you're moving at 95% of the speed of light, appears to take 9.61 seconds. And this gives rise to what is often called the twin paradox. And so if we imagine a set of twins, one named Speedo, not because he or she is wearing a Speedo, and the other called Go Slow, these twins in every way, one stays behind while the other gets in a spaceship and travels to some place 20 light years from the Earth, and somehow is able to travel at 95% of the speed of light. When Speedo comes back, he will find out that Go Slow Go Slow has aged by 42 years and is now 62 years old, even though Speedo has only been gone for about 20 years. They both started off at 20, but somehow Go Slow is much, much, much older. Now, the paradox is not that the twins age at different rates and end up at a period of time having different ages. Both of them If they were wearing the same wristwatch, their wristwatch would be operating and counting down the time exactly correctly for each individual relative to where they happen to be. The length contraction is that as an object begins to approach the speed of light, its length begins to contract or get smaller and approach zero. Once again, we have the same adjustment factor, the same Lorentz transformation here. But this time you can see that as the speed of light begins to approach c, v squared over c squared becomes 1, 1 minus 1 becomes 0, and the apparent length begins to approach 0. It begins to contract. It begins to get smaller and smaller. So if we had a meter stick and we began to accelerate it towards the speed of light, its thickness or width wouldn't change, but its length would get smaller and smaller and smaller from the perspective of an observer. And it would still have 100 centimeters, but they'd be closer together per meter. And if you want to see a math problem that shows that, you can do this problem right here, where once again, if we've got something traveling at 97% of the speed of light, how much is the length going to contract? And again, we make sure, like I said before, that if the object is accelerating this way, it's only its length contracts, its width does not change. Now, relativistic momentum, and momentum, of course, is mass times velocity, so we could talk about relativistic mass. We have our same transformation here. And once again, as my speed v approaches c, then v squared over c squared approaches 1. 1 minus 1 equals 0 in the denominator. And so my momentum begins to get closer and closer to being infinite. In other words, an infinite mass with a infinitesimally small length as time begins to slow down and appears to stop from the perspective of the observer. Now, this equation right here is just to show you that, let's say we had a rocket ship going this direction at a speed of sound, and we had another rocket going this direction at the speed of sound. I mean, it's not sound, at the speed of light. Sorry for that phone call interruption. That if you're observing over here on some planet and watching them, you will never ever see something moving faster than the speed of light. You could say that at what speed are they approaching each other? If this is moving at 0.9 tenths the speed of light and this is moving at 9 tenths the speed of light, it would be incorrect to say that relative to each other they are moving at 1.8 times the speed of light. That would be false. And you'd have to plug those values into this equation to see the error of your thinking. We won't derive that equation. Relativistic energy is where we end up with E equals mc squared. We have our rest energy, and then we have the idea that, according to this incredible insight on the part of Einstein, that it takes more and more and more and more energy to speed up something, and that amount of energy can be calculated like this, Again, as your speed of light begins to approach c, then 1 minus v squared over c squared, approaches 1, 1 minus 1 approaches 0, and as my denominator gets super small, the amount of energy gets incredibly large. In other words, it begins to take almost an infinite amount of energy to accelerate that mass anywhere close to the speed of light. Now, I should point out something very important, that at ordinary speeds, all of these Lorentz transformations, this is now our fourth one that we've looked at, all of our Lorentz transformations reduce to Newtonian ordinary mechanics at ordinary slow speeds, when v is very, very small compared to c, then Newton's physics works out just fine. All of these Einsteinian equations, when you make the assumption of a very, very, very small speed, v, end up being Newton's laws. Newton's laws are a subset or special case of Einsteinian theories of relativity. Now, that also raises the interesting question that is it possible someday in the future that Einstein's theories will become a special case based upon some other assumption? So, this expression, E equals mc squared, is universal. It applies to all objects and processes and systems. Please remember that c squared does not mean something is actually moving at the speed of light squared. It's a conversion factor. It basically means that energy and mass are two sides of the same coin, and that you can convert energy into mass, or you can convert mass into energy. And this happens all the time. In a nuclear reactor, for example, we take our fuel, often a 5% concentration of uranium-235 or some plutonium-239, and we see that some of that mass is converted into energy to generate electricity. So matter is converted into energy, and in the unit on nuclear physics, we use this equation all the time. We've also seen in something called a cloud chamber that gamma rays entering this cloud chamber with a vapor of, say, alcohol vapor or something in it will leave behind a trail, because sometimes gamma rays actually turn into particles that have a mass. A gamma photon is pure energy. And you can see the trail of that particle. So matter turns into energy, and energy turns into matter, and this is your proportionality constant. Now, this also means, by the way, that if you heat something up and you give it some energy, you've actually increased its mass. But that mass is way too small to even begin to measure. So we usually assume that the mass doesn't change. But if you had enough decimal places and the equipment able to pull it off, warming something up actually makes it have a little bit more mass. And that's a pretty radical kind of idea. And if mass is relative, then so is momentum. I should mention that when we get to nuclear physics, there is something called the electron volt, which is the amount of energy needed to move an electron through a potential difference of 1 volt. And you can see that it's not a whole lot of energy. That's an incidental comment made for future reference. And then finally we come to general relativity. Everything we've talked about heretofore is basically Einstein's theories of special relativity. And Einstein's theories of general relativity are a whole different way of looking at gravity. Whereas instead of thinking about gravity as being some property of mass, in which case we have these Newtonian ideas, we think of gravity as being some type of property that affects space. That what mass actually does is it warps space And therefore, when objects fall towards an object with mass, it's not because the mass and the gravity of that object is pulling it in, but it's because the object is falling towards the mass because the space has been warped or contorted in the vicinity of that mass, and the object is merely following the contours of that curvature. So when we think about general relativity, we've got these ideas. All the laws of nature have the same form for observers in any frame of reference. It doesn't even matter if it's accelerated or not. Before, it didn't matter if it was moving at a great speed or not. Now it doesn't even matter if it's accelerated or not. And this gravitational field might be better understood if we thought about an analogy. Let's say that in our classroom, we had a huge sheet of very, very thin, fine rubber, or even a bedroom sheet. So this is all a sheet. And we're holding it very, very tightly at the ends, so it's as flat as could be. And let's say we put a bowling ball in the middle, which will bend the sheet down, the sheet down. Now, if this person over here releases a marble, that marble will follow the contour of that bent sheet, that warped sheet. It'll roll down that contour towards the larger mass that's in the middle. And the larger mass in the middle will appear to be relatively unaffected by the very difficult to measure contour or warp of the sheet that the marble had caused. And this is a whole different way of looking at gravity. Now, by the way, neither of these models tells us what gravity is, just what it seems to do. Right now, they're thinking about a new quantum model of gravity, which would involve gravitons. But once again, that's going to explain how gravity operates, but it's not going to explain what gravity is, because it won't explain what gravitons are. And so once again, in physics, we have these ideas of energy and force and gravity and light that we describe and that explain many kinds of phenomena, but we don't know what they are. And this was the experiment that made Einstein extraordinarily famous, because he predicted that you would appear that a light star that you know to be here would appear to be here because a large massive object such as our sun would serve like a gravitational lens and would focus the light would bend that light towards the Earth. If the star happened to be in the right position, blocked by the sun, and of course this star would be many light years away from our sun, and it would appear to be very far away, and you would not be able to see it directly from the Earth. Mathematically, you would know it would be right here because you'd be tracking it based upon the motion of the Earth and the motion of the sun, but the star would appear to the Earth before it actually is visible from the Earth directly because of the bending of light by the gravitational pull of the sun. Now, how much is that bending? Not a lot. 43 arc seconds per century was the difference when they tried to observe Mercury. Mercury, of course, is very close to the sun, so you would expect it to be affected by Earth's gravitational pull, but Newtonian mechanics did not explain it. It explained it 99.999% of it, but not 43 arc seconds worth. It was off by 43 arc seconds. What is an arc second? Well, if you remember, there are 360 degrees in a circle, and each degree has 60 minutes, And each minute, we use dash for a minute, each minute has, let me erase that. Each minute, 1 minute, is 60 seconds, double dash, or double mark right there, like a quotation mark. So that is a very, 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 very small difference. And of course, you might say, oh, that's just the way nature is. That's as good as we're going to get. Or you can say, no, something's up there. We're not investigating this enough. Or if you're like Kepler, you would say, I don't think God is like that. I think there's an explanation for this discrepancy. And sure enough, there is. This also then led to discussions of black holes, things that are so massive that light not even does it no longer bend as it goes past that super massive object, but it bends so much that it can't even escape this supermassive object and is trapped by that supermassive object. Which means that if this is my supermassive object, there is a point of no return. That if something is entering and it passes this point of no return called the Schwarzschild radius, some distance r, Schwarzschild radius, that once you are that close to the supermassive object, the gravity is so great you cannot escape it. And of course, that's why the object appears to be black, because no light is escaping from it. The only reason we know that there is a black hole somewhere is because when an object is beginning to get inexorably pulled into the black hole, never to escape again, there is some radiation, X-radiation, that is emitted. Also, you see the word singularity, which means the laws of physics at this point begin to break down. In fact, we could say that black holes, the so-called Big Bang, and in fact, any moment, for example, throughout Genesis 1, where it says, and God said, let there be, and boom, something comes into existence, the laws of physics don't work there. We could call those singularities. Finally, you have the laser interferometer, not to be confused with the Michelson-Morley interferometer, which you could put on a desktop, but a laser interferometer, gravitational wave observatory, or LIGO. We've got two of them in the United States, one up in Washington, one way down here in Louisiana, if I remember correctly. And this whole thing then acts like a huge telescope, if you will, for gravitational waves. And all we need to have is one end and the other end, and we can pick up waves that are this long. Remember, a radio wave might be 1 to 2 kilometers long, a radio wave. So this would be a very, very gigantic wave, a gravitational wave. And we've had a few of those that we think we have detected with our LIGO. So that's an overview of this chapter.